Hello, and thanks for tuning in. In this video series, we'll go through a step-by-step mathematical derivation of the backpropagation algorithm, one of the key algorithms used to train neural networks. Our goal will be to arrive at these four equations right here. And don't worry, all of these terms, some of which are vectorized, will get explained as we go along. So let's get started. And just to give some context as to what backpropagation is used for, consider a typical neural network model. Such a network is a layered arrangement of artificial neurons where the layers can be indexed from 0 to capital L, 0 being the input layer, the capital L layer being the output layer, and the layers in between are referred to as hidden layers. Now this neural net serves as a mathematical function which takes in some input vector, performs calculations on this input vector from layer to layer, propagating it through the network and producing some output vector at the other end. Now if we zoom into the neurons which make up the building blocks of our neural net, a particular neuron V, or the VF neuron of hidden layer L, can be depicted as such. We have a neuron V here at hidden layer L, as well as all the other neurons from the previous layer. And all the neurons from the previous layer connect to neuron V through edges. Now, neuron V in and of itself is a mathematical function with some input and some output. And the input to neuron V consists of all the outputs from the neurons in the previous layer, which we refer to as activations. So these will be denoted as A1, L-1, which means the activation of the first neuron at layer L-1, and this would be A2, L-1, and this would be AN, L-1, assuming here that hidden layer L-1 has N neurons. And here we've assumed full connectivity. Every neuron in L-1 connects to neuron V. And this assumption will hold between any two adjacent hidden layers. So in order to obtain the input to neuron V, what we do is we take all these activations from the previous layer and we scale them by quantities assigned to these edges, which we refer to as weights. And the weights will be denoted as such. So the weight assigned to this edge would be W1VL, which essentially means this is the weight going from the first neuron in the previous layer to the VF neuron in layer L. This would then be V2VL, and this would be, WNVL. And so what we do is we take all these scaled activations, we add them together, and then we add an additional quantity, which is referred to as a bias term. So the bias term will be denoted as BVL, which is the bias for the VF neuron at layer L. And this bias term is added directly to the neuron. So what happens is we take this entire linear combination, and this linear combination has a special name, which we refer to as the weighted input. So the weighted input at neuron V of layer L would be the sum of the scaled activations as mentioned. The activations are scaled by the weight values. And then, as mentioned, we add the additional bias term. And then the final output, which is produced at neuron V, we get by taking the weighted input and running it through some nonlinear function, which we denote as sigma. So we run ZVL through this nonlinear function, and then we get some new activation term, AVL. L at neuron L. So the output of neuron V becomes AVL. Now back to our neural net. In a typical supervised learning setup, our neural net will be applied as a predictive model, where our goal is to tune it to provide accurate predictions on some unknown input. So this tuning or training process, as it's referred to, is a prerequisite for our model to provide accurate predictions, and it involves adapting the model to training data points. So what does this mean? Say we're supplied with a training data point as the ordered pair x1 to xn and y1 all the way down to yn. Here, x is some training input vector, whereas y is the expected output or response associated with this particular input. And y is known, that is key. And we can actually denote these as x and y just for compactness. So what happens here is we take x and we feed it into our neural net. So the x1 entry, x2 entry, all the way down to the xn entry. They're fed into the input layer. The neural net then produces a output predictive vector, which has entries y1 hat, y2 hat, all the way to yn hat. For compactness, we can refer to this as the yhat vector. Upon receiving a predictive output vector yhat, what we do then is we try to assess how close yhat is to our expected output vector y. And we quantify closeness here using what's known as a cost function. The cost function takes in both the predictive output vector and the expected output vector. And computes a metric distance between the two, which then becomes our predictive error. It means that our cost function, which we denote as C, is a function of our predictive vector yhat all the way down to yn. And by extension, it is a function of all the entries of yhat. So yhat1, and let me just include yhat2 this time, and yhatn. And these yhat terms, what they are, the entries here, they're really activations of the neurons of the output layer. So yhat1 would be equal to the activation of the first neuron of the output layer, denoted by capital L. And this would be A2L, and this would be ANL. So we can further state that C is a function of the activations at the output layer. So A1L, A2L, all the way to ANL. Now looking back at our model and the activations at the output layer, it is the case that every single weight and bias within our network has some sort of effect on the activations. If I go into my network and I alter the value of any edge, or I alter the value of any bias incident to a neuron, then this effect will propagate and change the predictive vector I get at the other end. Hence, we can decompose our cost function further into a function of all weights and biases in our network. So it would essentially be all the weights and all the biases within the network. And weights and biases are often referred to under the umbrella term as network parameters. Now you might be wondering, why is C also not a function of our input vector x and our expected output vector y? This is because what we're trying to accomplish is, by keeping our x fixed and altering weights and bias values, we're trying to get y hat as close as possible to our expected y. So we're really only in control of our parameters. Now, since the cost function computes our error, it stands to reason that we'd like our error to be as small as possible, as this equates to more accurate predictions. C is a multivariable function of our network parameters, and this leaves us with a calculus exercise of finding the combination of parameter values which minimize C. Now, in multivariable calculus, this is typically achieved by taking the derivative of C, or multivariable function, with respect to a parameter, setting it to 0 and solving for a parameter, and then doing this for every parameter. So we'd have the partial derivative of C with respect to weight 1, set it to 0, and take the partial derivative of C with respect to weight 2, set it to 0, and so on, and then do the same thing for biases. Take the partial derivative of C with respect to all the bias parameters. And so on. This becomes a rather difficult computation when you're dealing with billions of parameters, and therefore we resort to a different approach for minimizing C using an algorithm known as gradient descent. Now, this algorithm is out of scope for this video series, so we won't delve into too much detail, but gradient descent minimizes C using a special vector called the gradient of C, which can be formulated like this. The gradient of C is defined as a vector containing all the partial derivatives that we previously saw. So it would be partial derivative of C with respect to weight 1, partial derivative of C with respect to weight 2, and so on. And then we'd also include all the bias derivatives. So we would have the partial derivative of C with respect to bias 1, and a partial derivative of C with respect to bias. So we would have bias 1 here and bias 2 here, and so on. And then we'd have to extend the vector notation here. So we're just taking all the parameter derivatives and vectorizing them. Now here we no longer have to solve for these derivatives in terms of 0, but we do have to compute these derivatives. And we're once again back to dealing with scaling issues. How do we compute such a large number of derivatives? And that's where backpropagation enters the picture. Backpropagation is an algorithm which gradient descent employs as a subroutine to efficiently calculate all these derivatives right here. Therefore, our derivation of the backpropagation algorithm will be reduced to finding generic expression for each of these derivatives. And our strategy will be as follows.